lesson on time and frequency response focuses initially on circuits, but as we approach the end of the lesson, we get more into a general systems approach as opposed to a circuits approach. We're going to look at first order transient analysis, second order transient analysis, Laplace transform analysis, and sinusoidal analysis, and Bode plots and filters. Starting off, we like to review what an energy storage element is. There are two of them of interest to us. Inductors are energy storage elements, and so are capacitors. And if you have one capacitor in a circuit, you will have a first order differential equation. If you have one inductor, you'll have a first order differential equation. More an inductor, the order of the system can increase. And the reason we say can and doesn't say it always will is because you have to be very careful how you count inductors and capacitors. For instance, if in a circuit you had two inductors, the way we've shown these two, and this is 1 millihenry and this is 2 millihenries, you have two inductances, but it's still going to be a first order equation because the 1 and 2 can be combined into simply 3. However, if I had something like this happening, I now have a third order equation because the same current does not flow through these two inductors, they're independent. And this capacitor adds another energy storage element to the system. So, first order equations, one inductor or one capacitor. And as we go up to more inductances and more capacitances, it's conceivable you can have a higher order system depending upon the connection of the inductors and the capacitors. Let's look at capacitors first of all. And the capacitor is characterized by a circuit that looks something like this. Let's imagine we had a Thevenin equivalent, R Thevenin, V Thevenin, of some equivalent circuit. And to this we plan to attach a capacitor, C. Then we can write a very simple loop equation that says V Thevenin is equal to the current times R Thevenin plus the voltage drop across the capacitor. That'd be the voltage across here. But the current, as we know from definition, is given by capacitance times the rate of change of the voltage across the capacitor with respect to time. Consequently, I can insert that for I, and this equation becomes now VTH is equal to C dVc dt times R TH plus V sub C. So this gives us the loop equation. It's a first order differential equation. We very often will pull the R Thevenin out in front of this just for convenience, so we can see the variable we're solving for in this differential equation is V sub C. Now the solution to this equation given we have B dq dt plus CQ equals f of t, then the solution is Q of t is equal to AE to the minus t over tau plus, and we put here f of t, but we'll put it in quotes. And the reason we put it in quotes because this will be some function of f of t. This is the driving function. This is usually a steady state part. And this answer may be proportional to this part, but it's something that's related directly to f of t. The rest of this is characteristic of the circuit itself. In this equation, tau is a time constant, and it's given by the ratio of V over C. And in an inductive circuit, it would be the same as L over R. In a capacitive circuit, it would simply be RC for the time constant. Second example of a simple circuit. Thevenin voltage, V. Let's imagine this to be 10 volts. R1, 10 ohms. We have a switch, a resistor R2, which is also 10 ohms. And we'll put over here a, let's put an inductor. This inductor, L, 0.15 Henries.